In this video, we talk about session 9.3, Convergence of Series. So before we talk about this topic, we first give the definition of the partial sum. We define the partial sum as n of the first n terms of a series as n is sigma ai from 1 to n. It's the sum of the first n terms, a1 plus a2 plus an. So to investigate the convergence of the series, we need to consider the sequence of partial sums S1, S2, S3. If Sn has a limit as n goes to infinity, then we define the sum of the series to be that limit. So if the sequence Sn or partial sums converges to S, then we see the series converges and its sum is S. We write sigma n from 1 to infinity an as S if the limit of Sn n goes to infinity does not exist. We see that the series diverges. So next we give some properties that are useful in determining whether or not a series converges. So it's called convergence properties of series. So if we have two convergent series, and if k is a constant, then the sum of these two convergent series is still convergent. So sigma n from 1 to infinity an plus bn converges to the sum of these two series. And its constant multiple also convergent. Converges to k times the series. The second one, changing a finite number of terms in a series does not change whether or not it converges, although it may change the value of its sum if it does converge. The third property, if the limit of the term does not converge to 0, or limit of the term does not exist, then the series diverges. If we have a divergent series, then its constant multiple is still divergence. If k is not 0. So now we look at an example. We look at this series. The sigma n from 1 to infinity, 1 minus e to negative m, determine whether this series is convergent or not. So for this series, we have an is 1 minus e to negative m. So as n goes to infinity, this goes to 1 minus 0 is 1, as n goes to infinity. Since the limit of the terms is not 0, so by this property 3, we have this series must diverge. This series must diverge by property 3. By this property 3, the limit of the terms is not 0. The series diverges. Second example, show that the harmonic series one plus 1/2 plus 1/3 plus 1/4 diverges. To show this harmonic series divergence, the idea is to approximate this infinite integral, the integral of 1 over x from 1 to infinity, by a left-hand sum. So we look at it from the graph. One over x is this curve. Use another color. This is y is equal to 1 over x. Y is 1 over x. So x is this is 1, 2, 3, 4. So we approximate this infinite integral by left-hand sum, where the terms 1, 1/2, 1/3, 1/4 are heights of rectangles or base 1. So now we do the rectangles with base 1 and the height. The height is the left is the value of the function at the left endpoint. So we do this rectangle. It has base 1. Its base is 1. Its height is also 1. So the area for this one is 1. So the second rectangle to this kind of rectangle, the base is still 1. Its height is 1/2. So the area is 1/2. Base to the third rectangle, base is 1. Height is 1/3. So the area is also 1/3. So from this picture, we see that the sum of the areas of these 3 rectangles is larger than the area under the curve between x is 1 and x is 4. So from the picture, we have the sum of these 3, the sum of the areas of these 3 rectangles is greater than the integral of this function x from 1 to 4. So this is equal to line 4. So the same kind of relationship holds for the first n rectangles. So we have Sn is 1 plus 1/2 plus 1/3 plus 1 over n is greater than the integral of 1 over x from 1 to n plus 1. So this integral is ln n plus 1. Since ln n plus 1 goes to infinity as n goes to infinity, and this one gets arbitrarily large as n goes to infinity, so do the partial sums as n. So this one goes to infinity as n goes to infinity. Thus the partial sums have no limit. The partial sums have no limit. So the series divergence. Sorry, it's divergence. Yeah. So the method of this example can be used to prove the following theorem. It's called the integral test. Suppose an is fn, where fx is decreasing. Fx is decreasing and positive. If we have the infinite integral of fx from 1 to infinity, convergence, then the series convergence. If the infinite integral divergence, then the series diverges. This is called the integral test. This is very useful. Recall that in chapter 7, we studied this infinite integral, the integral of 1 over s to power p as from 1 to infinity. So this integral was convergent for p greater than 1 and divergent for p less than or equal to 1. So now let's look at the p series. This series is called p series, 1 over n to power p. Let's look at the convergence and the divergence of this p series. So first, if p less than or equal to 0, 1 over n to power p. This is n to negative p. So this one does not goes to 0 as n goes to infinity. So in this case, the p series diverges by the divergence test, property 3. So on the other hand, if p is positive, then we know this function 1 over s to power p is a positive decreasing function. For x greater than or equal to 1, and we can apply the integral test. Hence, in this case, we can see that the p-series divergence for p greater than 0, less than or equal to 1, and the convergence for p is greater than 1. Hence, we have the p-series divergence for p greater than 0, less than or equal to 1, and the convergence for p is greater than 1. So we can summarize we have found as follows. The p-series sigma 1 over n to p, n from 1 to infinity, convergence if p is greater than 1, and the divergence if p less than or equal to 1. We summarize the convergence or divergence of the p-series here.